In today's lecture, we will talk about some examples of the count data model. And we started to talk about the Poisson distribution. We talked about how to analyze the Poisson data using this BRMS package, right? Bayesian method. We are using, in the Bayesian class, we are talking about Bayesian model fitting and then model checking also, right? But all in the Bayesian context. The next thing we said, we found quite a bit of zero in the data set, and we found regular Poisson model is not able to capture those zeros. Therefore, we thought about fitting a zero inflated model. We talked about that zero inflated model and then fitting of the zero inflated model. It is also very simple, very simple. The model fitting part, you just write BRM, and then the formula is where you write Y. This is the response variable, and then in the formula you write affairs, which is your response, depends on whatever explanatory variables you want to put here on the right hand side. And then in the family part, you must write zero inflated Poisson, okay, and link equal to log link. And then you have the specification of the prior distribution. Now, if you are asked to write the model, this is not the model. This is just a syntax of your code. Do not write as your model. Your model is the following thing here. This is your model. Okay. And what is lambda I? Look, lambda I is still same. Lambda I is equal to e to the power beta 0 plus beta 1 xi. In the last lecture, I talked about this expectation of yi given xi under the zero inflated model. What you found is that it is equal to 1 minus omega times lambda I. 1 minus omega. Omega is the inflation parameter. It gives you more weight than the regular Poisson distribution. So that is why we call it inflation. Inflate the probability of zero. That is why we call it inflation parameter, omega. And expectation of yi given xi is no longer simply lambda I, as in the Poisson case, it is 1 minus omega times lambda I. And then I wanted to calculate variance of yi. It is expectation of yi square given xi minus expectation of yi given xi square of it. It turned out to be 1 minus omega times omega lambda I square plus lambda I. Let me write it again to show you that it is larger than the expectation. So observe that the variance of yi given xi equal to 1 minus omega times omega lambda I square. So it is expectation of yi given xi plus this positive part. So variance is larger than the mean. That means it captures over dispersion. Over dispersion means extra dispersion in the data that is not usually captured in the Poisson regression model. All right, so we got the Poisson zero inflated Poisson parameter estimates. are the posterior mean of the distribution of the corresponding parameters and the 95% confidence intervals. Confidence interval, but it is actually the Bayesian credible interval. Last time we talked about how changing the model change the effect of some of the variables. For example, previously when we fit the Poisson model, the gender had a significant effect. You saw that the credible interval did not include 0. That means it showed a statistically significant effect of gender on the mean. But in the zero inflated model, gender variable has a credible interval, includes 0. Therefore, it does not have statistically significant effect anymore. And you can see some of the changes. If you want to estimate from the fitted model, suppose you are interested in estimating probability, how do you do that? You can definitely use the predict function to calculate it, but just to show you how it can be done, suppose you want to estimate probability. What is the probability that yi equal to 0, given that someone's gender, okay, so male, and then age, let's say 30 years, okay, years married, maybe 2 years, and children, no children, okay, religiousness, suppose it was recorded as an ordinal variable. So suppose it has 1, the minimum value. Education was also recorded as, what was that? Years of education, okay, years of education and self-rating of happiness. Years of education, okay, so let's say 18 years, and happiness is 1, suppose. Happiness is 1. Happiness is 1. Probability yi equal to 0. Now, why I'm showing it to you? Because I want to show you how you can use the parameter estimates. It is not a black box. When you use code calculates it. Then you think that this is some kind of black box idea. I do not need to know that, but the thing is you can simply calculate it using your hand calculator. So it is omega plus 1 minus omega times e to the power minus lambda. What is omega hat? Omega hat is e to the power this is the Poisson model, and then zero inflated Poisson model is e to the power 0.48 divided by 1 plus e to the power 0.48, and lambda hat is e to the power beta 0 hat, which is 8.60 plus male, okay, male means it will be 0.58. right? Because male appears as the dummy variable. If it is female, then it will be 0 here, okay? Age minus 0.18 times 30, I said 30. And years married, 2 years. So it will be 0.36 times 2. And no children. So children, yes, means 0.74 and no means 0 times 0.74. Religiousness, 0.46. I said 1, religiousness. Education minus 0.28 times 18. Okay, and rating of happiness 0.07. So you take these things, do e to the power, and that will be your lambda hat. You plug in lambda hat here. You calculate probability y equal to 0 for this covariate value. But of course, this is a very crude estimation of this probability. Bayesians will not do this type of estimation, right? What they do, they sample each regression parameter from the posterior distribution, right? And then calculate for every sample, they will calculate lambda hat. They will calculate omega hat. So if they sample 1000 observations from the posterior distribution of all the parameters, including omega, then you have a posterior estimate of probability y equal to 0, 1000 times. So you have a distribution. And for that distribution, you can take the average value, posterior mean, that will serve as the Bayesian estimate. This is a plug-in estimate. What I showed you is the plug-in estimate, where you just plugged in the posterior mean. And okay, so this. Next, we calculate the marginal likelihood. Marginal likelihood calculation came out to be minus 54.25, and it is much smaller, much larger than the Poisson regression model. In the Poisson regression model, it was about minus 59. So the next model we want to consider is the negative binomial model. And negative binomial model is another count data model where the response variable can take values like 0, 1, 2, 3, 4, like that. Where do you fit that type of model? If you have count data such as if you want to model the number of ships arriving to a port during a day, okay? You can say during a day or during a week. You have to specify the time period. This is very important. You cannot make the time period flexible. If you want to model them, you have to fix the time period. So you can model that using the negative binomial count data model, Poisson model, or the negative binomial model. Okay. So suppose you want to see weather's effect, okay, on the number of ships arriving to a port, LA port, for example, okay, weather effect, number one. Then tariffs effect. Nowadays, we all talk about tariffs, right? Import tariff. And you can compare that effect compare the, so you can assess the effect over time, how it is changing. So this is one example. Oh, another thing is number of hurricanes hitting a coastline. During, you can specify the time period. During what is the best time? I mean, for hurricane season, it's maybe August to November. So you can record that for a particular region, for a particular time period. Suppose you want to see the weather's effects or some effect, okay? I recently heard that Alaska, southern coast of Alaska received hurricane and that created a huge flood. Alaska. So you can you imagine the hurricane is hitting in Alaska, that cold place? Hurricane happens in the warm water, right? Not in that cold water. So you can model that. You can see the time trend. You can see the effect of weather change and other things. So you can hook up a lot of examples of count data where this is appropriate. The outcome is the count data. So number of hurricane in a given year could be 0. It could be 1, 2, 3, 4, right? There is no upper bound. Similarly, the number of ships arriving to a port could be 0, 1. 0 is very unlikely, but it can happen. Remember, during the pandemic period, right? Sometimes there was no ships arriving to a port. So that is also possible. But important thing is this is a count data, count variable we are modeling. So why negative binomial? Negative binomial is a more flexible model than the Poisson model. Poisson model was very easy. Everybody understands, but it is a very restrictive model. It tells you that the mean and variance will be the same. But in real life, most often, mean and variance are different. Therefore, Poisson models is more appropriate. But one other thing is that Poisson model allows you the variance to be larger than mean. And in most of the count data scenarios, you have variance larger than mean. You have only few cases. I cannot think of now, but in my other class lecture, I have noted down some scenarios where you have variance smaller than mean. In those cases, then Poisson model is not appropriate. Poisson model is not appropriate, negative binomial model is not appropriate, then you have to think about some other distribution which allows the variance to be smaller than mean. But over here, this is the negative binomial distribution probability mass function. Okay, and obviously you do not need to remember this expression. I also don't remember the expression, but what I understand is that there are two parameters. One is omega, another is mu I. This mu I is the mean value of the negative binomial distribution, which is modeled as e to the power beta 0 plus xi transpose beta 1. So this is again the log link. If I take log of mu I get the linear predictor part, this part. And this omega is called the dispersion parameter. Okay. So when omega greater than 0, that means when omega greater than 0, that means this variance of yi given xi is larger than the mean part. Do not mix up this notation with the with the zero inflated models omega notation. There I also used omega, but that had a different interpretation. It was the inflation parameter. Here it is the dispersion parameter. 1 over omega is called the shape parameter. If you want to fit the model, use this BRM function of BRMS package, and it uses this negative binomial. You make sure you put the family equal to negative binomial, link equal to log link. This is in R code. If you use MATLAB or something else, Python, you may find some alternative code. Okay, I'm sure something will be there. Something will be there, but keep in mind, we are talking about the Bayesian method of estimation. So check the other programming languages have Bayesian estimation method. This is Bayesian estimation we are doing, not the frequentist estimation. I know a lot of softwares out there, they have standard or the classical estimation methods, but not all softwares have the Bayesian version. So here, look, for the negative binomial model, we are putting gamma prior on the shape parameter. Shape is 1 over omega. And we have these parameter estimates. For the negative binomial model, we also don't see any effect of gender because the confidence interval, the credible interval includes 0. Education seems not to have any significant effect, right? Education. Did we see any effect of education in the zero inflated model? No, we did not see it. Also, for the religiousness, we did not find any significant effect. So these all 4 predictor variables, they don't have any significant effect. Years married has some positive effect, right? What does it mean? It means someone is married for many years, likely to have more affairs. Okay. Age does not have a significant effect. Gender does not have a significant effect. So this one, only thing that I see is this guy, years married, and rating, happiness rating has nothing to do also, right? Let's look at the negative binomial model. Yes, all these factors. No. So look, for the negative binomial model, these 3 predictors have no influence, no significant impact, right? Because their credible intervals include 0, but the rating of happiness seems to have a significant impact here. That was not there in the zero inflated model. And over here, years married does not have any significant impact. And the shape parameter, this is important, shape parameter is 1 over omega, right? 1 over omega is 0.58. Remember, this omega is not the inflation parameter. Do not try to interpret it as a probability. This contributes to the variance. All right, so let us look at the marginal likelihood under this model. So marginal likelihood minus 49.84, which is again much larger than the zero inflated model. For the zero inflated model, it was about minus 54. So this is log likelihood I'm talking about. So when you talk about the likelihood, marginal likelihood, it will be e to the power, right? E to the power 5 is a very large number. So based on these three models, this is the best model. The negative binomial model gives you the best marginal likelihood. Like the zero inflated Poisson model, there is a model called zero inflated negative binomial. Within the negative binomial, you can also allow extra zero by putting more probability there. And that is called zero inflated negative binomial. And this is, we pay more attention to this scenario. Statisticians, because for account data, it happens often that we have more zeros than what you expect from any model, whether you fit a Poisson model, whether you fit a negative binomial model. Okay, now one may wonder, if you have more zeros, to capture that more zeros, can you not make the rate parameter, for example, for the Poisson distribution smaller, which will capture more zeros, right? Yes, you can do that, but that will also decrease the probability of non-zero values. But in your data, you have some non-zero values, right? So if you decrease the rate parameter, it will increase the probability of zero, but simultaneously it will decrease the probability of non-zero values. But in your data, you have non-zero values. You cannot ignore them. So you need to find a model which will capture your non-zero values as well as more zeros than what you expect from any Poisson model. Therefore, we need that inflation parameter. This count data model is also used for public health research, where we want to model how many people or how many times someone without health insurance visits the emergency center in the last 1 year. And this type of modeling has a lot of impact in policy making. So essentially what happens if people do not have health insurance, medical insurance, they may end up to the emergency center, which will increase the cost of the government or the people who are paying for their own medical insurance. That is the reason, you see, if I visit the emergency center, I have to pay $700, right? Now it looks humongous amount. Why? Because there are some people who do not have any insurance, so they get the free treatment, right? So in order to see what percentage of people needs to have health insurance or medical insurance, we need to study this behavior, like what percentage of students, what percentage of people are visiting emergency center, how often they are visiting emergency center, and so all those things. And if you want to model them in terms of age, gender, race, their health insurance status, then you include those variables as your explanatory variables or the predictor variables, and number of visits to the emergency as your outcome variable. All right, so this is, now let's move on to zero inflated negative binomial model. Now, how does it look like? We know the negative binomial model here. For the zero inflated negative binomial model, we will have probability y equal to 0 given xi. We'll have omega plus 1 minus omega times another component, and this component will be coming from the negative binomial distribution when yi equal to 0. And what is the probability that yi, this capital Yi equal to little capital Yi equal to 0, you just replace this little y by 0, then the first two terms disappear, right? This to the power 0 means 1, and here it is 0, 0 factorial, everything cancel. You only have 1 over 1 plus omega times mu I to the power omega inverse. This will remain. And that is the probability yi equal to 0 under the negative binomial distribution. So for the 0 inflated negative binomial, 0 inflated negative binomial, we fit the model, and you can look at the model parameter estimates. So here you see shape parameter is 1 over omega, and this zi is the e to the power zi over 1 plus e to the power zi is the inflation parameter. You need a different notation to denote this inflation parameter. Don't use omega anymore, because omega you have already used to denote the dispersion parameter. Let us calculate the marginal likelihood, came out to be minus 51.244. So it is larger. Sorry, it is this is the log of marginal likelihood. So the best marginal likelihood is for the negative binomial distribution, right? So negative binomial, among all four models, negative binomial distribution has the maximum marginal likelihood. So best model, that is the best model based on the marginal likelihood. Okay, now next thing is, let us do model checking. Let us do further model checking. One may wonder, what is the point of doing model checking when we have already declared the negative binomial model is the best model? Well, as I said previously, you cannot say this model is the best, because we considered only four models. Among the four models, negative binomial is the best model. Okay. Now I still want to check model adequacy of this best model. How do you do that? Using the posterior predictive distribution, which is y nu given the observed data, x observed and y observed. And the idea is, in order to find this one, we write the model for a new observation given theta and the observed data, and integrate theta with respect to its posterior distribution. We learned this posterior predictive distribution in our material chapter 2 or chapter 3. And from this line to the next line, we go under the assumption that conditional independence, right? Under the conditional independence assumption, we go from here to there. One other thing is, y observed is the main random variable. X is the given value. Predictor variables are always given. So you can keep it, you remove it, does not matter, but main contribution is for the outcome variable, y observed. And conditional independence means given the true parameter theta, your new value does not depend on the observed data. Given the true parameter, you always keep the true parameter. Then this one does not depend on y observed. Therefore, I omitted y observed. And in this expression, people generally omit the given covariate x observed. As I said, covariates are always given. Therefore, we do not usually write it. But for our better understanding, I kept it. So my plan is to sample new value, y new value for every given covariate value. So what I'll do, I'll draw, suppose 500 observations, okay, and for our given observed covariate data, x is the observed covariate matrix. Observed covariate matrix. And this is my observed data, observed affairs. I will sample this guy, y replication, y rep, okay, will be sampled. So this is the loop s is equal to 1 to s. What I do, remember the posterior distribution. This is the posterior samples, okay? Fit negative binomial. If I write this one, that stores my posterior observations. So for every posterior observation, I'm going to sample this y value. So for every posterior observation, this is the, I call it beta vec, calculate this eta. Eta is used to calculate mu, right? And then the shape parameter, then sample y value from this negative binomial distribution. What I did, I sampled this theta, look, this theta from the posterior distribution, right? Use this theta to generate, I use this theta in this model to generate new observation, okay? This is the technique. And how many I did? I did 500 times. And calculated mean value of those observations. And what did I do here? So this is the posterior predictive check. So this is the yes. So this one, I have 500 observations, right? 500 observations for y rep is a matrix with 500 rows. How many columns? Same as the number of observations in our data, right? If I had 40 observations in my data set, then it is a matrix. Y rep is a matrix of 40 columns and 500 observations. For every observation, every row, I'm calculating the mean. That is why this row mean and compare. So row means, how many row means I have? 500 row means, and plotted these row means here. And observed data mean. Observed data mean, this one, mean observed, is this red line. I wanted to check whether that mean value is towards one of the tail areas. If it is towards the tail area, that means there is a mismatching. But if it is not towards the tail area, that means there is no strong evidence of mismatching. So here I don't see it is lying on the tail area, this red line. Another thing I wanted to check the plot of the mean in the, so this is the plot of the mean. Okay, so next is I wanted to check a proportion of zeros for every sample. I have 500 samples. Every sample calculated proportion of zeros. So proportion of zeros here, look, for 500 samples, this is this. And for our observed data, proportion of 0 was 0.6. This is right here at the center, which is a very good indication that we do not have a strong evidence against this model. So we are doing it for our negative binomial model. Questions? Yes, go ahead. Speak up, please.
When you always test without test if what is the omega when you estimate it equal to 0, and then if we use zero inflated first, and then the omega estimated is near 0, then we will have a constant. I just
Okay, so let me try to understand your question. Your question is zero inflated Poisson distribution, right? Zero inflated Poisson distribution, and you want to what do you want to do with the zero inflated Poisson distribution? Oh, so you want to try without fitting Poisson distribution, you want to directly go to zero inflated Poisson, right?
when the omega equals 0, then the 0 inflated will be the Poisson distribution.
No, you can speak here. Come here and say it again. No, don't worry. Don't worry. We have enough time. Go ahead. Speak up, please. Speak up. You sit and speak up, please.
Yeah,
Yes.
I will show you because my speaking is not good. But this is zero inflated. It is a probability for y equal to 0, and I think if this one is estimated equal to 0, then it will look like the Poisson. So what if we just cover?
Okay, so yeah, so I think I got your question.
Yeah.
Let me answer this. So going back to this question, this was her question. If I want to calculate probability y equal to 0, I use this lambda hat, right? This lambda hat was calculated based on the zero inflated model's output. This lambda hat is not Poisson distribution's output, right? If I had used Poisson distribution output, then it would be wrong. Okay, so this lambda hat must be from the zero inflated models. All these parameter estimates are from the zero inflated model part. And another thing is, you said if this omega hat goes to 0, then your model goes to the Poisson model. Yes, absolutely. So if it turned out that omega hat is very small, very like 0.01 or something, then it turned out to be your Poisson model. Did I answer your question? Okay, we'll talk after the class about that. So no problem. Now for the posterior predictive check, I showed you two things. One, you can use mean, you can use proportion of zeros, but there is no hard and fast rule that you have to have these two statistics in use. You can use something else as well. For example, if you want to calculate some extreme values, like having more than 5 affairs, you can calculate that for your observed data, calculate that proportion, and calculate that proportion for every predictive sample, and see your proportion is within the distribution of the predictive distribution of that proportion also. And we did this thing, I believe, in another example that was also in the Poisson distribution example where we were talking about model checking. That time, we did not do zero inflated model fitting or the negative binomial model fitting. Now, another quantity often we use is BIC, Bayesian information criteria, for model checking. You may wonder, why do I need this BIC when I have already calculated the marginal likelihood? Yes, for the time being, for the problem, we do not need BIC because we have already calculated marginal likelihood. But suppose you have several other models and you don't want to calculate the marginal likelihood. Marginal likelihood is a very tricky calculation. It is not a straightforward calculation. It requires bridge sampling and careful sampling from the posterior distribution. Therefore, marginal likelihood sometimes is not feasible. What about using BIC? BIC has a very simple formula. And the formula is this: minus 2 times log of likelihood plus k times log of n, where k represents the number of model parameters, n is the sample size, and theta hat log of likelihood. Now BIC was originally defined where theta hat was the MLE, maximum likelihood estimator. It is an approximation, Laplace approximation of the marginal likelihood. Now, what do you do if you don't have MLE? In the Bayesian context, we do not have MLE. We have posterior mean, we have posterior median, we have posterior mode. So then you can replace theta hat by one of the three items and calculate the BIC value. And this is possible when you have a clear idea about the number of parameters. So here, number of parameters is k, then you can calculate it in a nice way. So for some simple models, this is very easy. Like in our model, we have a negative binomial model. We have a Poisson model where I have a clear idea about the number of model parameters. So if we have a Poisson model, then I know the number of parameters is includes beta 0 and all the components of beta 1. For the zero inflated model, it is the regression parameter vector beta 0, including beta 0 and beta 1, and the inflation parameter. So I have a very clear idea. But in some models, the number of parameters is not clear. Where? Such as in the hierarchical model. So there, we do not have a clear idea about the number of parameters. So here, let us calculate BIC using the posterior mean. So posterior, you have the posterior samples from the negative binomial distribution. Calculate the posterior means, just take the column means and calculate the log likelihood. In order to calculate the log likelihood, I use this D negative binomial log likelihood for the observed outcome. Psi is equal to psi is equal to this. Okay, psi means the shape parameter, and mu is the mean parameter. I put the suffix mean because I'm calculating it based on the posterior mean. And the formula is ultimately, so n, this is k, which is the number of regression parameters plus 1 for the shape parameter, and came out to be negative binomial. BIC negative binomial came out to be 162.37. Now, if you want to use posterior mode instead of mean, you can do so. And then your BIC value comes out to be 161.1127. So there is a difference, obvious difference, depending on the choice of theta hat. For this model, as I said, we don't need to because we have the marginal likelihoods. But in some cases, we are not able to calculate marginal likelihood due to computational issue, package not available. There we can use approximate the marginal likelihood calculation by the BIC value. And so for different models, we calculate BICs and choose the model with the lowest BIC value. What you can do for all four models, Poisson, zero inflated Poisson, negative binomial, zero inflated negative binomial, for all four models, you can calculate the BIC value and see whether the BIC is the least for the negative binomial model. That will verify that based on marginal likelihood, what you did is the right thing.